Thank you for the introduction, David, and thank you for the organizers to give a talk. I have actually never been to Lumini, so I was really excited when I was invited. I thought this would be my chance to make it, but I think now it just means that maybe in 2 years I'll be able to attend. So it's still on my list of things to do. But nonetheless, I'm excited to give a talk at this conference. I was not able to make it to the morning talks because of the 6-hour time change. So thank you for putting me at a later time slot. And I am going to talk about endomorphism rings of supersingular elliptic curves. And this will be joint work with Sean Hallgren, Chris Leonardi, Travis Morrison, and Jennifer Park. Oops, I think it wants me to agree to the meeting to be recorded. And then, okay. Sorry about that. Okay, so in this talk, I'm going to present an algorithm for computing endomorphism rings of supersingular elliptic curves. The running time of this algorithm under certain heuristics will be O of square root p log p squared. And so that's still exponential because the input size to the problem would be log p. And the outline in the outline of the talk, so I want to say a little bit about why this problem of computing endomorphism rings or supersingular elliptic curves have received so much attention again, and then present the algorithm after I give sort of the necessary background. This has also come up in the context of post-quantum cryptography, where the goal is to have public key cryptography that remains secure even in the presence of quantum computers. Now, why would we have to do anything? Well, the currently used cryptosystem, things based on RSA or on elliptic curve cryptography are all broken by quantum computers and also even certain special lattice type systems. And the question then is, and that is what post-quantum cryptography tries to answer, or what research in this area tries to answer, what the good choices are. So if there are some obvious candidates that are no longer good, are there some that are both secure but also efficient to use? And that's sort of the making both of these things work is sort of the key thing. I just said that elliptic curve cryptography in the traditional sense, where it's based on the discrete log problem, that's no longer secure in the presence of quantum computers. And so the new proposal is to instead base the hardness of the system on being able to find isogenies between elliptic curves. So the traditional cryptography that uses elliptic curve would be to take one curve, use the group law, and then you take multiples of a point, and you're assuming it's hard, if I give you the multiple of the point, to figure out what the discrete log, meaning the actual multiple that you took of the point. So that results in small key sizes, which was the appealing thing, but unfortunately, Shor's quantum algorithm breaks these systems. So in the new proposal, we're not just working with one curve, we're using an exponentially large set of elliptic curves, namely the set of all supersingular elliptic curves in characteristic P, and then the isogenies between them. And people have also already looked, and I think there is at least going to be one talk about this later this week, about doing the same thing, not just for elliptic curves, but also for higher genus and what sort of needs to happen. So the same way that the traditional elliptic curve cryptography was also generalized to higher genus. So, but that's sort of the state. And so here I've sort of made a table to show what sort of the systems are that could be used, and what the underlying hard problem is that these systems rely on. So RSA relies on the hardness of factoring, ECC relies on the hardness of the elliptic curve discrete log problem. Ring LWE assumes that SVP in ideal lattices is hard, and the supersingular isogeny-based cryptography, which I'm interested in, assumes that computing certain isogenies between curves is hard. And then there's also another system that was introduced by British intelligence that is a lattice system that assumes that it's hard to find, to solve the short generator principal ideal problem. So that's a problem in ideal lattices. But so that's just to give a variety of things. And so these isogeny-based systems have actually been around for a number of years now. So in 2006 already, Charles, Gordon, and Lauder introduced a hash function that is based on the hardness of finding isogenies. And then there was a proposal by Couvenye and independently Rostovtsev and Stolbunov that used ordinary elliptic curves. And then the supersingular version of that was proposed by Zhao and DeFeo in 2011. And after that, there's also another version that uses supersingular elliptic curves, but looks at curves defined over FP and at the FP part of the endomorphism ring, which then sort of more mirrors the system by Couvenye, but with the advantage that it's more efficient. So that's sort of what has happened. And in terms of the security, it's not known if isogeny-based cryptography is secure against quantum computers, but it's not even clear what happens classically. Before, so since this has all been so recent, before it's really possible to say something about security against quantum computers, it's really, we need to look at the objects and the hardness assumptions that are made in the different schemes some more, and maybe just start by studying these classically. So one question is whether or not the different systems, they don't all use the exact same hardness assumptions. Some are assuming that it's hard to compute isogenies. Some assume that it's hard to compute the endomorphism ring of a supersingular elliptic curve. Some assume that it's hard to assume the maximal order that is attached, that is isomorphic to the endomorphism ring of the supersingular elliptic curve. And one question is, are those questions all the same in terms of hardness, or are these problems of different difficulty. And so we looked at some of these and gave some reductions between the questions. And another question is also whether the objects that show up and that are sort of naturally computed during these protocols, if they actually have polynomial representation size. So just sort of as a basic first step. And also, well, even though supersingular elliptic curves can all be defined over fp squared, if you are in character, like if you're looking at a supersingular elliptic curve in characteristic B, it can be defined over a field of size p squared. But once you start computing isogenies, you may go to field extension, have to go to field extensions potentially, and that can result in exponential size objects. So it's not so the sizes of things can blow up if one isn't careful. And of course, in order to not make it possible to just search in polynomial time for the correct isogeny, the isogenies that are used in cryptosystems have exponential size, and like a key feature one or key problem one has to solve is to decompose this into isogenies of smaller size and then find those. So, and that's done through the l-isogeny graph. So here, let me just look at an elliptic curve E, and we have some map phi here that's going to be an isogeny that respects the group structure, and these isogenies are determined by their kernels, and I'm assuming here that my isogeny is separable, in which case the degree of my isogeny is just the size of the kernel. So here I'm trying to get from an elliptic curve E to E prime via some composition of isogenies. And so, for example, if I just say I want to do the easiest case and I just want to look at two isogenies to other curves, that I can do because the isogeny is determined by its kernel. There are three subgroups of E of order 2. And so modding out by the subgroup of order 2, I get to another elliptic curve E1, and then to a second elliptic curve E2 and a third elliptic curve E3. And these I can just explicitly compute. So there are, well, so what's the hard part? If I just give you two curves E and E prime, I have to show that they're actually, I want to say find an isogeny whose degree is 2 to the n. So that means I want to concatenate a bunch of isogenies of degree 2, starting from E, until I hit E prime. And the first question is that even possible? If I use only two isogenies, is the graph even going to be connected if the points in my graph are the supersingular elliptic curves in characteristic P? The answer to that is yes. The graph is connected, but the question of how to get an isogeny between two arbitrary elliptic curves like that, it's not known how to do that efficiently. So, so that means, so if I'm only interested in isogenies of a certain prime power degree, like let's say L, and L is small, 2, 3, 5, 7, so L is going to be tiny, whereas P is going to be a graph of cryptographic, prime of cryptographic size. So P is huge, has several hundred bits, and L is tiny. And so we're choosing some small prime. And then we're looking at what is called the supersingular l-isogeny graph, where we take the vertices to be supersingular elliptic curves up to isomorphism, and then we just connect two of these vertices if there is an l-isogeny between the two curves that represent these. So, or we could like label the points on the graph by J invariance, for example. And so that we know there are roughly p over 12 supersingular elliptic curves in characteristic P. And because L is small and fixed, we can efficiently compute neighbors. And we also know that GL is an expander graph, or even more strongly, a Ramanujan graph. And so that means that finding isogenies now just becomes a path-finding problem in this exponential size Ramanujan graph. So that means, and so the question is, when we're looking at these questions, when we're looking to find these isogenies, so one thing we could just do is we could just see what kind of graph theoretic algorithms are there that just work with expander graphs and just find paths in these expander graphs, or can we do something better knowing that these vertices actually correspond to supersingular elliptic curves? Right, and so as I've already said, so the reason why this has attracted so much attention is that these recently proposed systems that I mentioned assume that it's hard to compute isogenies between arbitrary supersingular elliptic curves. And it's also possible to show that if you can compute endomorphism rings, then you also can compute isogenies. So that means, so the way I phrased it on the slide is I said computing isogeny reduces to computing endomorphism rings. So you can also use the knowledge of the endomorphism ring to construct these isogenies. And so that's why I'm looking at the endomorphism ring problem here. So I'm going to take an elliptic curve defined over a field of characteristic P. And just to recall the definition again here, I'm going to say that E is supersingular if the endomorphism ring is an order in a quaternion algebra, since I'm in the, right. So, and if you just look at, I think even Silverman, he only talks about the endomorphism ring being an order in a quaternion algebra. But in fact, the endomorphism ring is not just any order, it's actually a maximal order. And we also know in what kind of quaternion algebra it is a maximal order. It's usually referred to as BP infinity. So by that, I mean the quaternion algebra over Q that's ramified exactly at P in infinity. So that means there is a basis here of 4 elements. So I'm writing it like as a vector space. I'm just writing it as Q plus Q gamma plus Q delta plus Q gamma delta. So that means the fact that the endomorphism ring is an order inside this quaternion algebra, it means that it's going to be a Z module and it's going to have rank 4. Yeah. So we have a rank 4 Z module inside this object BP infinity, which is non-commutative, and that's sort of where all the interesting things happen. And so David, who introduced me, is of course the one who first studied this problem of computing endomorphism rings, both in the ordinary setting and in the supersingular setting. And the algorithm that he gave in his thesis was a breadth first search algorithm, also in the isogeny graph, to find cycles that then generate something of finite index in the endomorphism ring of E. So that means, so why are cycles interesting? Well, if we have a cycle in the l-isogeny graph, that means we have a map that starts at some elliptic curve E, and then we compose a bunch of things and we end back at E. So that means a cycle in the l-isogeny graph corresponds to an endomorphism, a map from E to E. And so that means you could just like start by saying, let's just generate a bunch of cycles until we generate the whole endomorphism ring. And there is a paper by Galbraith, Petit, Chani, and T that explains that sort of heuristically, we would expect log P calls to a cycle finding algorithm until we have the full endomorphism ring. So by sort of making the endomorphism ring bigger by generating more and more endomorphisms, i.e. cycles in the isogeny graph. That's sort of not the route we go, but we still also rely on cycle finding algorithms. And then the question is, how hard is it actually to find cycles in this l-isogeny graph? And so this was analyzed by Delfs and Galbraith, who gave an algorithm in 2016 that runs in time O tilde of square root of P. And so what does our new algorithm do? Well, it still generates cycles. So it finds two cycles that generate a subring of finite index. So in the picture that I'm giving here, my starting vertex is E, labeled by the elliptic curve E, or it's J invariant J0. And then I have the black cycle alpha through J0. And then I have the green cycle beta. And so what I want to do is I want to generate two cycles that generate, first of all, an order. And it should have finite, so it should be a subring of finite index. So I want an order inside end E. In fact, so I didn't write it in this step, but the key idea that'll show up when I explain the algorithm in more detail is that we're not just generating any subring here inside end E, but we can actually kind of control things so that the two cycles that we're using generate something that's called a Bass order inside the endomorphism ring, which means that locally there won't be that many orders that are bigger than the order lambda that I already have. And then rather than generating more and more cycles until we have the whole endomorphism ring, instead what we do is we work locally and just find locally all the maximal orders that contain lambda. And so that means in step 2, once we're done and put everything together, we have a candidate set of all maximal orders inside BP infinity that contain this order lambda that we found in step 1. And so that's, and then the last step is, once we have this candidate set O1 through On, then we know since the endomorphism ring of the starting curve E is a maximal order, it means it must be isomorphic to one of these orders that are found in the second step. And now I just have to figure out which one it is. And the whole point of this is that if I just take any lambda that has finite index, then the set that I find in step 2 might be giant and might be of exponential size, and I can't really do something with that. But if I'm putting more restrictions on lambda in step 1, then the set of orders I'm finding in step 2 is smaller, and the algorithm performs better. Yeah, so then the third step is, as I already said, we have to figure out which of these OIs is actually the endomorphism ring of E. So we know the endomorphism ring of E is a maximal order in BP infinity. We found some subring lambda. We figured out all the rings that contain lambda, and then we figure out which one of those must be the endomorphism ring. And so here, without the picture, when I'm just stating it again in algorithm form, the key property that we're using is that the order we're generating in step 1, we want that to be a Bass order. And I'll talk about that a little bit at a later step. But that's the property that guarantees that the local steps are going to be efficient, at least. But the first thing is still that we need to come up with a cycle finding algorithm. And so just like the other algorithms, we're going to have to come up with cycles in the isogeny graph that then will correspond to endomorphisms. And so and we do have a new cycle finding algorithm. But to explain how this works, I want to just sort of talk a little bit about how a generic cycle algorithm would work just in this graph theory setting. So we have a Ramanujan graph. And what that means is that when we take a random walk roughly of length log p, we'll end up at a random vertex in the graph. So that means after we do that, we can just iterate that. So we're going to end up with a roughly uniformly random vertex in the graph. And now I think it's often referred to as the birthday paradox. If your graph has a certain number of vertices and you are able to compute by using these random walks, uniformly random vertex in the graph, then you can figure out how many times you have to repeat this so that you get a collision. And so the answer is you have to repeat it roughly square root p times. The only issue is, well, and so that gives you the cycle, because once you have a collision, so in this case, I started at J0, I did a blue graph, I did a blue random walk, a green one, a black one, a purple one, and a pink one. And the purple one and the black one were ended at the same vertex. And then I concatenate the two. So if I think about things as being directed, then I concatenate the first one with the reverse of the second one, and that gives me a cycle through J0. The only thing I have to do here is I have to store all of the paths, because until I find a collision, like two paths that end in the same vertex, I'm not sure yet which one of the paths that I found previously is going to be the one that I want to use, because I sort of generate more and more and more paths that have more and more different endpoints. And then one of those is going to be the winner. But in order to sort of go with this, use this algorithm, I have to store all of the paths. I don't know a priori that the black one is the one that's going to be matched by the purple one. And so that means the runtime I can compute is square root p log p squared. But the space complexity is also very large because I have to store these square root p paths. And so that means it's both exponential in the running time and the space complexity. Now, we're able to cut down on the space complexity, but we're still, but the running time sort of stays the same. And what we're doing is we're still going to take random walks of the same length, log p. We're starting at some vertex J0 as before, but this time we're going to stop generating random walks when the final vertex of our path is adjacent to the conjugate vertex. So here our J invariants are the J invariants of supersingular elliptic curves defined over fp squared. If the curve is defined over fp, the J invariant is in fp, and that means J is just equal to J to the p. If the J invariant, if the curve is only defined over fp squared but doesn't have a model over fp, then that means the J invariant generates a degree 2 extension of fp, and so that means to each J invariant, then I also have what I call the conjugate J invariant, J to the p. They're the ones that both have the same minimal polynomial. And so why am I interested in this? Because if I have a path from J0 to JK, I also have an associated sort of conjugate path that ends at JK to the P. And then the only question is whether or not the black vertex JK and the black vertex JK to the P, of those two are neighbors. So that means if I found a path where JK and JK to the P are neighbors, then I can concatenate these two paths and find a path from J0 to J0 to the P. And then I can do the same thing again and get this orange path, a second orange path. And once I put those together, then I get my cycle. But so here, I don't have to keep all of my intermediate paths because I know that my black path is going to be the winner if I do my random walk of size of length log p, and it ends up at that at some vertex jk, and I check the neighbors, and lo and behold, jk to the p is also a neighbor. So that means at that point I can throw out all the previous paths, or like I can discard a path where that's not true, and I only have to keep the black path where it's true, and then I just find a second orange path. Because all I'm looking for is another path from J0 to J0 to the P. Now, there are some special cases where J0 is already in FP, and it gives a slightly different analysis. And it's not, so it could be that on this black path, one of the vertices might be defined over FP, in which case I really need to glue them together. But this is sort of what the generic picture looks like. So that only gives me one cycle, the black path concatenated with the orange one, and then I can do the whole thing again and get a second one. And I can also add some conditions on the cycles to ensure that I really get an order in terms of making sure it's enough to ensure that one of the cycles omits a vertex and the other one has in it. And if the cycles have a certain property in terms of not having self loops and things like that. And so in order to analyze the running time of the algorithm that I just described, we have to sort of answer the question of how often does it happen that some J invariant J and its pth power, so the conjugate J invariant, that they actually are neighbors in the l-isogeny graph. So this was also a question that was asked in another paper, and Adventures in Supersingular Land. And so what we showed is that under GRH, we get square root p over log p curves that are adjacent to their conjugates in this graph GL. And once you know that, then you sort of can plug it into the whole machinery of how many random walks you actually need until you hit one of these curves. Because now you know overall you have p over 12 vertices. The property that you want is this fraction of the the theorem tells you what fraction of the vertices have this property. And so we can show that, so you still get square root p log p random walks. And that means the running time overall is still exponential. But in this case, the space complexity is only log p, because we only need to store the current path and we don't need to keep around any old paths. Okay, so let me just briefly say something about the second step. So now we're assuming that we're done with step one, and I'm going to say something about this Bass property in step two. So now we have an order in the endomorphism ring, and now we want to make it larger locally. So an order, it's just the subring of our endomorphism ring that has rank 4 and finite index. And what we really want to do here is we want to solve a local version of the problem, meaning we want to tensor our orders with ZQ for some prime Q. Yeah, so I'm picking Q for a prime here because L is my, because I'm looking at l-isogenies, so the L is already taken, and P is my, the characteristic of my field that I'm working over. So running out of letters, we're working with primes Q here. So that's why we have the labeling of the primes here. And so the discriminant lambda of this order that we find in step one tells us where we even have to do anything, because locally the lambda that we find will already be maximal unless we're at a prime that divides the discriminant. So that means we only have to do work at finally many primes. And so what we're doing is we're using the Brouillard-Hitz tree. So that means we're using the fact that locally here we can represent our ZQ order. So we can we just start at some maximal order in this Brouillard-Titz tree. And so what we need is one maximal order containing lambda q. And then using the machinery of the Brouillard-Titz tree, we can find all the other ones because of we're gonna use the fact that the maximal orders are gonna lie on certain paths, namely that if I have two maximal orders, which are represented by vertices in the Brouillard-Titz tree, then everything on the path between those two vertices are also maximal orders that contain the given one lambda q. So that sort of means once I look at this local situation, I sort of have to find one maximal order that contains lambda q, and then I'm sort of just exploring the tree. I can efficiently compute neighbors to find all of the other maximal orders that contain the given order lambda q. Well, and the efficiency of the algorithm depends on how many of these orders there actually are that contain lambda q. So and so one way to give the definition of a Bass order is to say order is Bass if it contains CQ cross CQ or the ring of integers in a quadratic extension of QQ, and then our overall order lambda is Bass if it's Bass at every completion. And it turns out that if you work with a Bass order, then you can actually bound the maximal orders that show up in this local step. So the number of local maximal orders that contain the given lambda q is just bounded by 2 times of the exponent of q that shows up in the discriminant of lambda. So that means if you factor your discriminant, it tells you the exponent just 2 times that exponent just gives you an upper bound of how many of these you end up finding when you're traversing the Brouillard-Titz tree. And since finding neighbors in the Brouillard-Titz tree is efficient, that means the algorithm to find all the maximal orders locally is ends up being polynomial in just log of the discriminant of lambda, because all we really need is the because the number of things we compute is just the exponent of q that shows up in the discriminant. So that means this local step is good, but recall we already our first step, when we actually found the 2 cycles, that was already an exponential size step. So even if everything else now were efficient, we'd still have an overall exponential algorithm. But so nonetheless, so this step can be done efficiently. And then the last question is how we actually get all of the maximal orders that contain lambda. And so because now we have, for all the primes dividing the discriminant, we have a set of local maximal orders that contain lambda q. And now we want to come up with global ones. And the idea here is to just, it's possible to just do the step-by-step. So first so you use the local case answer, what I just described in the previous step, to find all the local guys. And then you can take sums of the things that you found in step 1 to compute global maximal orders that will contain your given order. And so at this point, we're in a situation where we have all the global maximal orders that contain the given order that we found. And now we know that the endomorphism ring should be one of the ones that we found. And we just have to figure out which one. And so that means that sort of amounts to the following problem. Well, so we have a supersingular elliptic curve. It's the curve E that corresponded to the J invariant J0. That was our start vertex in this graph exploration through which we found the cycles and everything. And now we have a bunch of maximal orders in BP infinity. And we want to know which one of these is the endomorphism ring. Well, it is possible to do the following, namely, we can take one of the maximal orders that shows up in our list, and we can compute a curve that has that endomorphism ring. So that was done in prior work in a paper that appeared in Eurocrypt. And so that means, so what happens if I construct a curve E prime whose endomorphism ring is O? Does that mean that must be the correct curve? Or, sorry, does that mean, well, so now sort of two things can happen. Now I just have to see if the J invariant of the elliptic curve E prime that I found matches the J0 that I started with. And if it doesn't, it would still be okay if the pth power of it matches up, because J and J to the elliptic curve with J invariant J and the elliptic curve with J invariant J to the P, they both have the same endomorphism ring. So that means in the second step, all I do is I compute the J invariant of the curve E prime, and I just check whether it's equal to this J invariant of E, which I'd call J0, or the pth power of it. And if that's the case, then that's the right endomorphism ring. And so that means what I have to do is I have to go through the list one by one. There's sort of no, it's just exhaustive checking at this point there. Yeah, so. And so I already mentioned it in words. And so, yeah, I'm just using the fact that two supersingular elliptic curves whose J invariants have the property that one is a pth power of the other, that their endomorphism rings are isomorphic. Yeah, that's like the correspondence between endomorphism ring and J invariant. It's not one-to-one. When the J invariant is defined over fp squared, it's 2-to-1. Yeah, that's the fact I'm using. And well, so the running time is the same as the running time of the cycle finding algorithm. So that's the bottleneck, is already the first step where we found the two cycles. And the question this time is not how often do we have to generate cycles until we have the whole endomorphism ring, but this time we want to know what's the probability if I generate two cycles that I actually get one of these orders that are Bass. And there is a condition that just expresses this in terms of the discriminant, and in experiments this happens after a few attempts, and if you assume some heuristic about how the random these cycles are, then you can actually just bound this, say exactly how many you need. And then we're able to bound the number of global orders containing lambda when the discriminant is square free. That we can do, we can just compute what that is. But when the discriminant of lambda is not square free, we need to put in some heuristic. This is maybe like a point where like someone with more analytic number theory could help to just prove that straight out, what the number of orders would be that contain lambda in the global setting when we put it all together. But so we were only able to do that in the square free case. And the bottleneck is still the cycle finding algorithm. Since we're only doing this, computing these two orders and 2 cycles and then go from there, we're still saving a factor of log p over the algorithm that generated log p cycles to compute the endomorphism ring. And so just to summarize things, our algorithm uses a cycle finding algorithm that connects J invariant to its conjugate. And then we work with orders both in the local and global setting to enlarge the order lambda that we found that is generated by the 2 cycles that we found in the first step. And this is the running time of the algorithm. And one question is it possible to remove the heuristic assumptions that we have to put in there? And I think the big question would be if there's a polynomial time cycle finding algorithm. I think that would have big implications for the overall security of these systems. But that's sort of where things stand. And I'm gonna stop here. Thank you.
Okay, thank you, Kirsten. Are there any questions? In the chat, just if you have a question or put up your hand. Yes. Okay, I don't know who, Valentine or Marco was first. Let's start with Valentine. She's.
Sure. Yes, thanks, Kirsten, for a really interesting talk. I had some small questions about the local part where you were finding the local maximal orders. Because if I understood correctly what you said about the Borat-Titz tree, then we still need to start by finding a first one. And
yes.
I was wondering how you do that, and also how you then really know that you found them all, because you gave an upper bound, but when do you know that you're really done?
Yeah, so the finding the first one, that's a class, that's something that was already solved by, I forget who it was who solved that problem, but I think it's John Voigt. I think it's the paper identifying the matrix ring. He found a way to compute one maximal order, and his algorithm is efficient. So that means we can use that as the starting point. And and I think you can actually, so I gave an upper bound, but but that's only because the upper bound is only because in the local setting, there are sort of different cases that are being distinguished, which can sort of show up. And once you know in which case you are, you actually know the exact number. So that's sort of, I just sort of summarized everything, this statement uses a paper of Brzezinski on quaternion algebras, like sort of 3 different cases, and I just summarized them all together by taking the max value. But yeah.
Thanks very much.
Okay, and Marco?
Yeah, so I was wondering, so you go to in the path, you find a path to a J that is next to its conjugate.
Yeah.
What if you, aren't there also about square root J's that are actually in FP? Wouldn't that give the same running time?
Yes, so you can, in the paper, we sort of look at a more general picture. So you're absolutely right. You can look at ending in a J invariant that is an FP. You can also end in one where it's not directly like that, sort of a path of length 0 to the adjacent, like J to the P. We looked at path of length 1. You can also do, how about if it's only 2 steps away, things like that. They all give the same asymptotic running time. It just turned out that when we landed in a J invariant that it was in FP, when we went to like the formal analysis of the proof, there were like a lot more subcases to consider. I mean, I think it will work out exactly the same way, but the random graph stuff, yeah, the other case was much easier to analyze, or was much cleaner to analyze. But you're absolutely right that the number of things in FP is the same. It's only the extra conditions that I need to impose that I didn't really talk about, because I need to make sure that the second path I have uses a vertex and doesn't do something else. And that was somehow, it seemed much messier in the FP situation.
Thanks. Can I ask?
I guess these are all just giving a constant increase in the size of your square root of P sets, no?
What does?
Go ahead, Marco. Oh, each one of these contributions, the order square root of P, Z adjoint square root of P, Z adjoint square root of LP, these all give class number big O of square root of P contribution to the possible endpoints.
Yeah. Right, and the number of curves in FP, supersingular J invariants in FP, that's already known. And then sort of the, and then the, like the new part was that the endpoint that we chose was a set that has also not, whose size had not previously been analyzed. Yeah.
Yeah. You had another question, Marco?
Yeah, I had one other question, which is, so you compute all the global maximal orders that are candidates, but there are also so these endomorphism ring computation algorithms that you sometimes that are pretty old for ordinary curves, also of higher genus. I see that there people compute locally whether the local maximal order is correct by computing whether certain potential endomorphisms really are endomorphisms by looking at torsion. So that would be the Q torsion in your case. Would that work here as well, or is there a real reason for computing all the global ones and then checking all of them?
So I don't think we were able to just compute it based on like a piece or something of the local piece, because our global step usually like actually says, well, let's just find a curve that has the correct and has one of these endomorphism rings, and then see if it's the one that we were given, or up to like p power. And so I'm not sure. I mean, yeah, that is sort of, that would be like the like a more elegant thing if you could already go into the local case and say, well, all of these are out because of some local consideration. I think we tried that. I don't know if we are able to do that. In the end, we were sort of, I think, a little bit discouraged because the bottleneck is really the cycle finding algorithm. And so it seems like you would get the biggest mileage by somehow, if you were able to improve that. Yeah. But that would still be an interesting question. And I don't think we were able to do that. Yeah.
Yeah, thanks.
Okay, are there any other questions?
Sorry.
Sorry, was someone else speaking?
I think Kirsten was speaking herself.
I was just going to add that in some cases you can exclude things, but I don't think we found something where like that worked for every single thing that showed up. Yeah.
Maybe some of the ideas of Gaëtan-Bisson's work for commutative orders, since you're basically looking at the whether a given commutative suborder exists inside of the endomorphism ring. You might be able to just push that forward.
Yeah, that's an interesting idea.